Hi, Yasmina. Hi, everyone, and welcome to this webcast. Thank you for being here today. My name is Tarik Soulami, and I am the author of Inside Windows Debugging, which is a book that was published earlier this year by Microsoft Press and O'Reilly Media. And I'm also a full-time employee at Microsoft, where I work as a development lead in the Windows division. Earlier in my career, I also spent several years in the Common Language Runtime team in the .NET group. And today I will be covering an important class of bugs, commonly known as heap corruptions. If you are a C or C++ developer, you have likely seen these bugs before, and you know how difficult they sometimes can be to investigate. If you are a managed code developer, you are protected from these bugs to a certain extent by the managed code environment provided by the CLR, where all pointers to memory are considered as safe. However, if you have done any interop with native code where you've had to call native components in your managed code, then you have probably hit these bugs too when you were trying to craft your first invoke declarations or call interop invocations. So this talk will be interesting, will be useful to both native and managed code developers. So we'll cover both angles in this presentation. If you have the Inside Windows Debugging book already, the content of this talk will essentially mirror section 2 of chapter 8, which is titled Common Debugging Scenarios. If you don't have the book, that's fine. I will try to introduce all the concepts, all the necessary concepts before applying them. Later in this presentation, there will be a few demos where I will be sharing my desktop with you so that I can walk you through a couple of experiments to illustrate the concept. Before we get started, and we talk about how to debug native heap or managed heap corruptions, I'll be spending a few minutes talking about some basic concepts, about specifically what it means for programs to crash and why memory corruption is such a bad class of bugs and such a challenging class of bugs to debug. And then from there we will move from general memory corruptions to the heap memory corruptions, which is a special case of memory corruptions, but it's a very important special case because a large majority of crashes, of program crashes in Windows, and probably in other platforms too, is due to heap memory corruption. Memory corruptions in general and heap memory corruptions in particular. So let's talk about that a little bit. So what's a heap first? I mean, that's I think the first question is, what is a heap and what is a heap corruption? So before we talk about heap corruptions, so a heap is essentially just a region of memory where dynamic allocations can occur by applications. So if you have used malloc, new, or any of the other common allocators, even column allocators, for instance, then that memory is called, the memory that's placed in that region of code is called a heap. And when that region of the code gets corrupted, then you get random program behavior. And if you are lucky, the program crashes. If you are not that lucky, the program starts behaving erratically. Now, one of the most challenging aspects of debugging memory corruptions is the fact that they're hard to reproduce. I mean, that's issue number one. Before you even get to debug them, you have to be able to reproduce them. And sometimes you don't get, you might see a repro only once, and there And then if you try to reproduce the problem again, nothing happens. I mean, the program just seems to work properly, and it only seems to crash under very specific scenarios where maybe the load or the load on the computer increases, or under stress conditions and things of that nature. The second challenging aspect of debugging memory corruptions is the fact that even when the program crashes, it doesn't actually crash right away. It can crash way after the point where the bug occurred. And the reason for that is that programs only crash when they attempt to access memory that hasn't been committed. So memory in Windows, in programs, is committed in pages. And if you try to access a page that hasn't been committed, so a page typically is a 4K. So if you try to, 4 kilobytes essentially. So if you try to access memory in a page that essentially is not committed, the program will crash. But if you try to access, let's say, a freed buffer, for instance, a freed buffer is that memory could get repurposed for another variable or another use in the program, and the page might be committed, so the program will not crash, but you still have a problem. You still have a very serious problem, and that's why the crash occurs unpredictably. And it will occur sometimes, and if you are not careful enough to actually catch it and investigate when it occurs, it might only occur when your program is used by your customers. So the main idea in debugging corruptions, memory corruptions, is the following. And this is a very important concept that I would like you to think about, because it will actually come, we'll see it in practice throughout this talk. And that is that in order to debug memory corruptions, and heap memory corruptions in particular, we need debugging hooks that allow us to force the program to crash closer to the source of the bug. Without that, it becomes harder to track down where the memory corruption occurred, because, as I said before, the program might only crash way after the point of the corruption. So now that we talked a little bit about memory corruptions, I would like to just point out that in this talk, I'm only going to be talking about a very particular case that's very important nonetheless of memory corruption, and that's heap corruptions. So in a process, you can have a multitude of bugs that corrupt memory, and you could corrupt stack memory, you could corrupt all kinds of memory. But in practice, heap corruptions are very, very common. And so that's the purpose of this talk. The book, Inside Windows Debugging, covers other cases of memory corruptions, but we won't be talking about them in this particular talk. We will focus on heap corruptions, which is, according to statistics that Microsoft collects from crashes, the heap corruptions are actually 2/3 of program crashes. So they're very important, a very important category of bugs. All right. So we talked about what it means for a program to crash, and when the program crashes due to access to invalid memory, that's what is called a memory access violation, which makes sense because it's access to this memory that caused the program to crash. And we'll see a few examples of that later in this talk. So now that we have this foundational knowledge about what it means for a program to crash and what it means for it to crash due to heap corruptions in particular. We will talk in the rest of this talk, we will talk about two categories of heap corruptions. The first one is native heap corruptions. That's essentially heap corruptions when you use the C++ new allocator or the C runtime malloc allocator or the con allocator. So all these they boil down to the same type of heap corruptions at the end of the day. And then later in the talk, we will also talk about GC heap corruptions. GC standing for the garbage collector heap, which is the main heap used by .NET programs, which is provided by the Common Language Runtime, the CLR virtual machine. So with that, let's talk about native heap corruptions. So there is good news when it comes to native heap corruptions. So the main thing that I would like you to take away from this talk is that native heap corruptions are actually not that difficult to debug if you are able to reproduce them. And the reason for that is that there is a very good instrumentation support for debugging native heap corruptions in the operating system, and you can use that to with very good results if you are able to reproduce the bug. So let's say you have a crash, and you realize the crash might be due to some dangling pointers that you have in your code, in your C or C++ code. And if you are able to reproduce the bug, if the bug is reproducible, then it's really easy to find out which buffer is being corrupted. If the bug is not reproducible, which can happen, if you have a very complicated scenario where the bug only, like the corruption only occurs if you take a very particular code path, like a rare code path that's not taken in the normal execution of the program, then the main issue, the main issue there is not necessarily to debug the problem. The main issue becomes, how do I reproduce this problem? And then once you are able to reproduce the problem, it becomes actually just you can just use the machinery that we are going to describe now with the page heap and the application verifier, and you are good to go. You are well on your way. So in this case, we're going to assume that you can reproduce the problem by rerunning the scenario. But it's not difficult to do that. And the good news, the good news here is that no matter what allocator you use in your code, whether it's malloc, new, or other allocators, they're all built on top of what is called the NT Heap. So malloc, free, sysalloc, string in the COM allocators, local alloc, global alloc, heap alloc, all of these allocators, they call down to the NTDLL layer and the NT Heap implementation. These allocators implement some additional, they implement their own layer on top of the NT Heap, but the core memory management routines are provided by the NT Heap. What this means is that if the NT Heap, if it's easy to diagnose memory corruptions at the NT Heap level, then you are good to go, because all of these allocators use the NT Heap, and you are good. And the good news, as I said, is that there is a very good debugging implementation of the NT Heap, debugging hook in the NT Heap that allows you to do just that. Before we talk about that, before we talk about this particular debugging hook, which is called the page heap, a very important concept in this talk, I'd like to just present you with a few examples of memory crashing. You might be asking yourselves, okay, is it really easy to have memory like heap corruptions in your program? Is it easy to have these type of bugs? And the answer is absolutely. I mean, it's very easy, and even the best programmers have these kind of bugs, can fall victims to these type of bugs. And obviously, you have probably seen off-by-one bugs are very common in C and C++, where you end up writing past the end of a buffer or before the beginning of a buffer. Doesn't necessarily have to be off by one. It could be off by several bytes. And those are called buffer overruns and buffer underruns. Very nasty category of bugs. Double frees are very common. So it sounds like they shouldn't be common, but they are, unfortunately. Use of a buffer after it has been freed is another case of, another very common case of heap corruptions. And another one that I see a lot, personally, is just like using either accessing the null pointer or using uninitialized memory. And it sounds quite easy to actually avoid these kind of bugs, but it's not. I mean, in reality, you might be telling yourself, well, I'm never going to use a heap buffer before I initialize it. But in reality, you have some pretty complex initialization schemes that developers come up with. For instance, they could come up with asynchronous initialization, asynchronous initialization routine, maybe because it's a very time-consuming routine, so they might be initializing the global variables on an asynchronous thread, and then all of a sudden they get a call back onto their main thread, and they try to access the variables before they have been initialized. So these type of bugs, while they seem easy at first to avoid, in practice they are not that simple to avoid. So that's something to keep in mind here, that even the best developers make these mistakes. Okay, so now we get to the meat of this particular part of the talk, which has to do with the native heap corruptions. And I would like to talk to you about the page heap. So the page heap is, hands down, the best debugging aid for native heap corruptions. And we will see an example of that with a demo later in this talk. So what is page heap? Page heap is essentially, as I said, it applies to the NT Heap manager layer. So it's something that's provided by the Windows operating system. The application developer doesn't have to do anything to instrument the code in order to use the page heap. It's already there. The only thing that an application developer needs to do is just enable page heap, and then all of a sudden you get all the benefits of the page heap instrumentation. The page heap actually is not just a debugging hook in the NT Heap manager. In fact, it's really a parallel implementation of the heap. It's really another implementation of the NT Heap that you can substitute in place of the NT Heap, and which allows you to have better control as to when a program will crash, when memory corruption occurs, and things like that. So as I said, page heap is the best way to track down native memory corruption, heap memory corruptions. And what's the main idea behind page heap? So you have, let's talk about what kind of, so we saw the examples for how heap memory can be corrupted. Basically, one of the cases, for instance, is you write more bytes than the buffer can hold. So you write past the end of a buffer, or you write past before the beginning of a buffer, for instance. So writing past the end of a buffer is far more common. And as we said, that's not going to cause the program to crash right away. And the reason is because you might be still within the same memory page when you write after the end of a buffer, and that's not going to cause the program to crash. As we said, the program will only crash if you try to access non-committed memory, a non-committed page. But if the page is committed and you are just writing to some other region in the page, not your region, obviously, you are corrupting the page, but that's not going to cause the program to crash. But as the program continues to execute, well, the program is likely to crash later. So that's the main challenge that we had starting this talk. And the page heap addresses this issue. How does it do that? It addresses this issue by placing each allocation on its own page. And it actually places the allocation at the end of the memory page. So by doing that, it ensures that if you write past the end of the page, and then what it does is it has 2 pages actually per allocation. It places the allocation at the end of page number 1, and then the adjacent page after it is reserved but not committed. So what this means is that if you write past the end of the buffer, even an off by 1 byte, just 1 byte at the end of the buffer, you will be writing to the second page, the adjacent page, which is non-committed, and the program will crash immediately. And you will be able to catch the program in the act, so to speak, when that off by 1 bug occurs. So that's very, very good because now you know exactly where the memory corruption occurs. There are a couple of drawbacks for using page heap. In practice, you won't get bothered by these drawbacks, but there are cases where they might actually be a problem. Problem number 1, which is pretty obvious from just the description that we gave for page heap, is that, well, even if you allocate just 2 bytes of memory, well, you are using actually 2 pages for each allocation. 2 pages is, if each page is 4 kilobytes, that's 8 kilobytes, even if you are allocating just 2 bytes every time. So you'll be using a large amount of memory in your scenario once you enable page heap. And that's why page heap is not enabled by default. And the other thing that we talked about in the beginning is that you need to rerun the scenario because page heap is enabled per process and it's enabled when the process is started. So you have to be lucky enough to get a repo after you rerun the scenario. And that's a common problem that we have when debugging memory corruptions in general and heap memory corruptions in particular. In practice, if your scenario is small enough, you won't even notice. This will only become a problem if you have an application that's heavy in its memory use, and but by turning on page heap, you start either running out of address space, program address space, in the case of the x86 platform, 32-bit, or your program starts crashing too much to disk on 64-bit. On 64-bit, you won't run out of virtual address space, but your program might start crashing to disk too much because of the heavy memory usage. So in the full page heap, this is the picture. So we have 2 pages. The first page is where the allocation happens, and then the second page is the additional guard page where that is not committed, and that it's called the guard page because that's where if you write just 1 character or 1 byte after the end of the buffer, that guard page is going to cause an access violation because it's not committed and you're trying to access non-committed memory there. There are a few details that are not obvious at first, but the main idea is what I just described. The actual user buffer, so the pointer that you get is that user buffer there that's depicted in this slide. It's aligned to the end of the first page. You have the additional guard page after that, and then before the user buffer, there's also what is called a block descriptor, and that block descriptor is very useful because it allows the page heap implementation to keep track of, for example, when this buffer was allocated, and things of that, or if it's freed, when it gets freed. Now, I think we have done quite a bit of theory here, and we have talked quite a bit of about the theory of page heap. So I think now is a good time to maybe go and look at this in the debugger and see how it looks like. So I'm going to talk now about a case. Let's look at the case where we have a use after free. So I'm going to share my desktop now with you so that we can walk through this together. So we do that. Right, so let's take the following program. So this is a very simple program. But yeah, so we have a main function here, and in this main function we initialize some shared state, this FT parameter. We allocate a string, other words, and then we pass this shared state to multiple threads. We create a lot of multiple threads right here, and we don't wait for those threads to terminate. That's the issue here. We don't wait for the threads to terminate, and then we exit the function. Okay, so it looks innocent enough, but there is a serious bug here, which is that when we exit the function, the smart pointer FT parameter is going to be automatically destroyed, and as a result, the string buffer is also going to be deleted. But the threads that we create are, this is the worker thread, are trying to print the test message that was passed to them. So they might end up using this buffer after it has been freed. The key here is that this will not always be the case because it depends on when the main function exits in relation to when the worker threads exit. So if the worker threads are all done by the time that part of the main function exits, then no crash will occur. And this is why I have this sleep here just to increase the probability that the crash will occur. And this is always the problem with, so this is a very common case in heap corruption. You have a case where it's not you don't have a consistent repo. So the key here is that if you run this program, yeah, it looks like it's running fine now. I mean, so this time the first time it ran fine. The second time it starts displaying garbage. So now you start. This is the first sign of a memory corruption. When you start seeing garbage like this at the end of the that means you are trying to access an invalid memory location. And you can see that, okay, the program doesn't crash. It does not crash. It just starts behaving erratically. And this is the worst thing about memory corruption, is that if you are not careful, you might never actually realize that the program has started behaving erratically. Okay, so now let's enable page sheet. So it's very easy to enable using app-verifier. The application verifier is the de facto tool of choice for debugging native programs. So when you see, now I see my program behaving erratically, I suspect memory corruption. So what I do is I go and enable the application verifier for my program. So you could either use file add application, or you could use the Ctrl-A shortcut here, and you just add the name of the application. So it's just the name, not the path to the application, it's just the name here, the name of the image. And that's it. Okay. And I run the program now. So that's all I did. I just enabled app verifier. That enables a bunch of debugging hooks, among which is the page sheet. So that's the key here. And all of a sudden now, okay. So I have a crash. So you can see now that this is crashing in the debugger. And so you can see that once I'm in the debugger, I can just fix the symbols as usual with these two commands, symfix to fix the symbols, and reload to reload the symbol. And now I can display the call stack at the time of the crash. Okay? So I can see the call stack is happening inside of the worker thread when trying to printf the message. Okay? So that's cool. There's a very cool debugger extension that goes with the application verifier that's called app verifier, and it will give me some more details about what is going on here. So I'm lazy. I don't want to go look at the function I was doing, so I will just use @verify. And this is very good. And it will tell me a lot of information here. And the key here is this first paragraph, and it will give me a command to run. So it will tell me heap-p-a, and the address that I was trying to access. So this is this invalid address that calls the exception. So this is the address that I was trying. This is the memory address in the decommitted page that I was trying to access. And if I do this, it will actually tell me what this address is supposed to be, was supposed to be in the program. And what it's telling me is that it's an address that was freed. So now I know that I'm trying to access an address. So if I just dump the bytes around this address, this same address, you can see these question marks. These question marks are the telltale sign that you are in a non-committed page, memory page. So what happened here? What happened is that I'm trying to printf this message, which has already been saved. The cool thing about this heap extension command is that it tells me exactly when it was freed. The page heap kept track of when my memory location was freed, and it's telling me that it was freed when it gets freed. It was freed by the wmain function when this smart pointer got freed. So now I know which buffer we are talking about here. I mean, I can just look at the code now, and the code, if I go back to the code here, so if I go back to the code, I can see clearly that this is the main function, and this is the buffer that we are talking about. So this allowed me to essentially track down what buffer got corrupted. And from there, I see what the bug is. So let's go back to the slide now. Okay, so this was a cool example. And as you can see, all I had to do was enable the application verifier and run the application, and hope that I would get a repro. Where in this case, I got a repro because this code path is the main code path for the application, so I was going to get a repro anyway in this case. So I have a 100% repro. This is awesome because I wasn't even near that without the page heap, and before I enabled page heap, I was sometimes getting successful runs, sometimes I was getting garbage printed. I was never actually able to get a crash without the page heap. So with the page heap, I was able to get the crash, and from the crash, I was able to go back to the code site of the memory corruption. So we talked about this heap debugger extension, and it's a very cool extension that goes with the page heap implementation. It understands the internal structures of the page heap. So when you do then heap -p means you are requesting page heap information, and -a is essentially the address that you are interested in. So you do then heap -p -a, and then the address that you were trying to access, and the extension is smart enough to tell you what page heap block this address was supposed to be in. And it will tell you whether, because the page heap keeps track of allocations and deallocations, it will tell you whether this block is currently freed. So that was our case in the experiment here, or allocated. And if it's allocated, it will tell you the allocation call stack. If it's freed, it will tell you the free call stack. And that's exactly what it did last time. It told us when that buffer got freed. So, as I mentioned, full page heap has some limitations, and chief among which is the fact that it consumes too much memory. There is an alternative to full page heap called light page heap, and you can also enable it using the application verifier. The main difference between full page heap and light page heap is the following: is that there is no guard page in light page heap. Instead, what light page heap does is that it puts, so the key is that we still want to be able to catch off by one byte. So if you write past the end of the buffer, for instance, we still want to be able to catch that. And we were able to catch that with the immediate access violation in the case of with the presence of the guard page that wasn't committed. That was very good because we were able to catch it in the act. When we were trying to write past the end of the buffer, with light page heap, that's not going to be possible, but then we will get the next best thing. And the next best thing is we will catch it when the buffer is free, instead of when the actual memory corruption is occurring. And the trick there is that what light page heap does is it puts an extra fill pattern, so a well-known fill pattern, at the end of the user buffer. So this way, if you write past the end of the buffer, that fill pattern can be verified when the buffer is freed, and if it doesn't match, it will tell you that, hey, some corruption occurred here. And it will tell you when the buffer was allocated because, as we said, both full and light page heaps keep track of the allocation call stack of the buffer. So it's not, you will know when the buffer was allocated. You will not know exactly when it was corrupted. That might or might not be an issue. In simple cases, it might not be an issue at all. I mean, you will just go and review the source code and find where the corruption occurred. In more involved cases, it might be a little bit more challenging, but at least you get something. At least you get, at least you know which buffer caused the corruption. So you have a starting point for the investigation. My recommendation is to just use the full page heap unless you see that either your app starts crashing too much or there is too much memory. Chances are you won't run into any of these issues in the majority of cases. So my recommendation is just use full page heap, use app verifier to enable it, and you are well on your way to catching native memory corruption. Okay, so that concludes this section of the talk, and the next section is going to be about GC heap corruption. So what do we mean by GC heap corruption? The GC heap is essentially the area of the heap. It's a heap area also. So it's like the native heap, except it's managed by the CLR virtual machine. So when you have a managed program, a C# program, you write C# or VB.NET or whatever. You write your code in your language of choice, and then what happens is that your process, your user mode process, hosts the CLR, and the CLR takes control of the execution environment of your code and allows you to write your code with some safeguarding in place. So it would not allow you, for instance, to write past the end of a buffer, like it's possible to do with native code. So that's all good. So in most cases, if you write your code with pure C# code, for instance, you won't need to worry about heap corruption. That's assuming, of course, that you trust that the CLI itself, which is native, doesn't have any bugs. So with that assumption in mind, you are good. You don't have to worry about heap memory corruption, unless you need to interoperate with native code, which is a very common case. A lot of applications need to call into existing code that was written either with COM or existing with its two APIs, for instance. and they need to either p-invoke to those necessary APIs or COM interrupt into the COM component. So what's the main difference between, so when you do a new of an array in C#, you do new by 50, for instance, in C#, that array gets put on the GC heap. When you do new of an object, same thing. So the object in the CLR gets placed on the GC heap. So the GC heap is completely unrelated to the NT heap. It's not built on top of the NT heap. So that's a very important remark to make, because what this means is that the page heap is not going to help with GC heap corruption. So that's unfortunate. The GC heap uses a completely different paradigm for allocating and freeing memory. In a sense, it's simpler than the NT heap because it just allocates objects sequentially on the GC heap, so it just allocates them one after another, and then it bulk deletes them. It reclaims this memory in bulk when doing garbage collection. And garbage collection happens periodically, so even if the object is not used, it might still be occupying memory on the GC heap until the garbage collector decides to go and reclaim this memory, and it does so in bulk. So it reclaims all the dead objects. So from this, it's actually we can derive that we can't use page heap to investigate these memory corruption that happen at the boundary from native to managed code, but we can still use the idea of page heap. So what was the main idea behind page heap? The main idea was that we were going to try to force an access violation right at the site of the corruption. So try to catch the corruption closer to the source. So we'll try to do the same thing with the GC heap corruption. How can we try to catch corruption closer to the source? So one of the main challenges with GC heap corruptions that sometimes makes them even harder to debug than native heap corruptions is that the garbage collection, when garbage collections occur, objects can be displaced on the GC heap. So objects can be moved around. For instance, if the garbage collector decides that it's in its best interest to go and compact the heap and reduce fragmentation. So with that, it might, by the time you get a crash, so by the time your program tries to somehow access non-committed memory, you might be dealing with objects that are completely unrelated to the object that was corrupted at first. Completely unrelated, because the object that you were dealing with probably went somewhere else, and then the memory location that now is being accessed might be holding a completely different object. So that makes it almost impossible to track down where the corruption came from unless you use debugging, the debugging hooks that we are going to be talking about just now. So the key here is that how can we catch the corruption close to the source? So the 99% case of GC heap corruptions occurs with p-invoke. So that's what we are going to be covering in this talk. There is another case that can happen also when you use unsafe C# code. So if you use unsafe C# code, you could be accessing memory pointers. You can then use raw memory pointers, and all of a sudden you are exposed to the exact same hazards that you are exposed to with C++ code. So those can be quite tricky to track down. But the main case is when you are calling into native code or coming back from native code to managed code. So when you are calling back from native code to managed code. So fortunately there is a very good hook to force a garbage collection to happen at these boundaries. When the garbage collection collector runs, it actually verifies the heap. So before it moves objects around, it verifies that the heap looks sane. And if it sees that an object is not sane, that an object looks corrupted, it would pop, and it would crash right there. So that's good. That means that now, because the GC collections, if we can force GC collections to happen at these boundaries, we can catch the corruption exactly when it happens. So that's the same idea that we use with page heap, except with a different method to catch the corruption closer to the source. So as I said, some GC heap corruption examples are listed here, and we will maybe focus on the t-invoke case in this talk. So how can we force these GC collections to happen on native to managed and managed to native transition? That's the key here. We can do that using what is called a managed debugging assistant. So managed debugging assistants are in a way debugging hooks in the CLR, at the CLR level, and they allow you to customize the behavior of the CLR to debug particular issues. And there are two MDAs, in short, managed debugging assistants, that are of particular importance in this case: GC managed to unmanaged and GC unmanaged to managed transition. So that tells the CLR to force a garbage collection, even if it doesn't need to, even if because garbage collections usually happen when there is pressure on memory, or there are some heuristics in the CLR that drive when garbage collections occur, because they're quite expensive, and so it doesn't make sense to attempt them more often than needed. But with these two hooks, there will always be a garbage collection attempted at these boundaries, and so the garbage collector will try to verify the state of the heap before it displaces any object. So that allows us to catch the state of the corruption closer to the source and not have to worry about objects getting moved around before the program eventually crashes, if we are lucky, or if we are unlucky, just starts behaving erratically. So I'm going to share my desktop again with you now to show you an example of an incorrect p-invoke declaration. So let me do that. And okay, so let's go to. So this is an example actually from the book. So it's a simple example, and here's what it does. So it essentially it tries to read the title of a notepad window. So simple enough. So it calls this API gets Windows text. It passes the max count, and the max count is essentially the buffer size that you are passing. In this case, the buffer size is 8 bytes. But then there's a mistake here. It's actually passed 256. So it claims that the buffer is 256 bytes long, when it's actually, in reality, it's only 8 bytes long. So what would happen is that if the title is larger than 8 bytes, we would have a buffer overflow, and we would get a heap corruption. In this case, a GC heap corruption, because we are corrupting the GC heap region of the process address space. Okay, so let's look at what happens if I just run the program like this. Okay, so I have actually a notepad window that's called untitled. So what happens here is that I have the second line. The second line here shows the first 8 bytes from that title, but so it looks like the program is working fine, but unfortunately I have corrupted the heap in the process too. So as you can see, the same symptoms occur as in the native heap corruption cases, and that means that I'm not always going to get a program crash. As a matter of fact, the program doesn't crash at all in this case. It's very unlikely that the program will crash, but if I have a lot of other buffers in the GC heap and I have a more complex program, well, what will happen is that at some point either the program will crash or you will get erratic behavior, well, unpredictable behavior. So if I were to just go and, so I can delete this and enable add verifier for this, it won't matter at all, because as I said, the GC heap is not built on top of the NT heap, so the page heap doesn't help in this case, and you can see that it has no effect on the application. So what we need to do instead, to force the corruption to happen closer to the source, is to use these NDAs that I just described. And in this case, it's actually pretty simple. You just add this config file under the same path as your managed application. So I have these two assistants, and I'm just enabling these two NDAs, which tell the CLR to perform a garbage collection at managed to unmanaged and unmanaged to managed transition. So there is another thing that even with this, it's not this NDA. These NDAs will only take effect if I also set this environment variable to 1. So now that I have set it to 1, and now I have something cool. So now I have a crash. So that's very nice. So now I'm able to crash the program consistently, which is good. So now I have a repo. I have a 100% repo rate, and I can debug what's going on here. So I will skip symbols again, and as you can see, there is a very interesting call stack here. So it looks like the crash is happening in the garbage collector code in the CLR. I mean, it's here, but this is the telltale sign of a bug in the application. So whenever you have these call stacks, it doesn't mean that the CLR is the one at fault. It just means that the application might have corrupted the GC heap. And you can see here, further down is this trigger GC for NDA internal. So that's part of the CLR. So now we are going through the code that's triggering the GC on our invoke invocation. And what's happening here is that during the garbage collection, we get a crash because the heap has been corrupted. And to see what managed function caused this, we would use a very common debugging extension called the SOS debugging extension, which is part. Okay, and I can use this command from the SOS extension, /stack, which will tell me exactly my function. It will tell me exactly the p invoke that's in progress at this point, and that's test.get window text. That's my so that's the one that just go there, and that has the incorrect declaration. And now I know that this is where the corruption happened. All I have to do is go and review the source code and figure out that, hey, I'm passing the wrong size in this p invoke code. So now we have been able to track down the source of the GC heap corruption. And with that, I would like this concludes the talk.
We will say a very big thank you to you for presenting a great webcast for us all. We thank all the attendees that attended today's webcast and hope you benefited from it. Again, we'd like to remind you all that Tarik's book is the O'Reilly Deal of the Day. Visit O'Reilly.com. You can't miss it. It's right there. Thank you, Tarik. Thank you, everyone. This will conclude today's webcast. Goodbye, everybody.
Thank you. Thank you.